So with this in mind, we can now actually go in a with this recapitulation of this with this recollection, we can actually just go into this one dimensional chambered flame of this coupling function formulation. So then this is the problem derivation as a problem definition, as you have seen that on the left hand it is a one dimensional flame, okay, and on the x axis we plot distance and on the y axis we plot both the fuel mass fraction as well as temperature. Of course these are different axes, axis properly has to be chosen, and then on the left hand side you have the fuel region, but it is not pure fuel. On the right hand side you have the oxidizer region, but it is not pure oxidizer. So then the mass fraction of this thing essentially becomes this is the mass fraction on the left hand side, which is given by YF0, and this is the mass fraction on the right hand side for the mass fraction of fuel on the left hand side, which is given by YF0, and this is the mass fraction of oxidizer on the right hand side, which is given by YOL. And then of course then I can define the boundary conditions that at x equal to 0 your YF is essentially is equal to YF0 and your Y0 is equal to 0, because this is the boundary that is at x equal to 0, that is on the left hand side your YF is equal to nothing but YF0. On the right hand side but on the left hand side on this boundary they have no oxidizer, because the entire oxidizer has been consumed any time after any point beyond xf your oxidizer has been consumed. So on the left hand side your oxidizer is equal to 0, your product oxidizer is equal to also 0, and your temperature on the left hand boundary is equal to T0. Okay. So on the right hand side similarly you have YF is equal to 0, because the entire fuel has been consumed after the reaction sheet, and but your Y oxidizer is nothing but Y0L, that is once again this is not equal to 1, because there can be some nitrogen mixed with the, it can be air where you have often nitrogen mixed with the oxidizer. We are talking in very general. So on the left hand, and also your product is equal to 0 and your T is essentially equal to TL on the right hand side. Alright. So with this we can do a coupling function for formulation. Of course you see that there is no flow, so we do not even have to invoke the assumption that your convection is less important than diffusion. But on the straightaway it is on, also of course it is a steady flame. So essentially your unsteady term, the time the dou T term goes away, your your divergence of rho U yi or rho u hs this type of terms go away, and you are essentially left with a balance of diffusion and reaction. And then of course we can do this what we just did in this thing, and we arrive at this coupling function formulation for apply immediately. We can apply this formulation in this case, and we have this Laplacian is also now dissolved into is simplified into just a one dimensional dou 2 bi dou x squared is equal to 0, and your beta I essentially now can be straight away solved into in two integrations as a linear function of x. So beta I is nothing but C1I as a constant and C2I, but of course beta I can be like, there can be different i's for fuel, there can be, because your beta I is nothing but nothing but your T tilde plus yi tilde. Oh, by the way, we also assume that the Lewis number is equal to 1 here, so this denominator of yi tilde goes away. So it's essentially T tilde plus yi tilde. Now then for beta we can have a beta f is equal to T tilde plus yf tilde. We can have a beta O as that is, this is for the fuel, this is for the oxidizer. We can have a T tilde plus yo tilde. Okay, so there can be two betas essentially, and then of course we have to use that because we want to invoke these boundary conditions. So this coupling function formulation, what we have here, we can this is essentially contains the information about the temperature within the system. It also contains information about the mass fraction within the system, mass fraction within this domain, and we can now what we to move further, we need to basically apply the boundary conditions here. Okay, and we need to apply these boundary conditions to obtain these constants. So applying this boundary conditions, what we get is essentially that we get that beta f is essentially T tilde plus yf tilde, okay, and yf tilde, that is our beta. We assume that the beta 1 is equal to essentially beta fuel, and that is given by T tilde plus yf tilde, and then if we apply this sort of things in here, we get this, and we get yf tilde 0 plus T0 tilde plus TL tilde minus T0 tilde minus yf 0 x tilde. Of course, it has to be linear in x. Similarly, with applying this, we get this boundary condition. So you should do this simple this on your own, and this will give you the confidence to basically solve for any kind of flames later. So this is what we have arrived, and you see that this result is in general. Okay, we have not limited to a reaction sheet. Why? Because I mean, we have not invoked any assumptions about the how large the reaction rate is in comparison to diffusion, etc. Okay, now will come where the reaction sheet approximations will be incorporated. So this is where we apply the reaction sheet approximation. That is, we assume that if this was our flame, this is the left boundary yf0, this is our right boundary where you have yol, and this is our T0, this is T, and this is our TL, and so this is, we assume that this yf goes to 0 at the flame location. Okay, this is 0. Similarly, we say that y0 goes to yo goes to 0 at the flame location. So in this region there is no fuel, and in this region there is no oxidizer. So this is only possible when the reaction sheet assumption is incorporated. That is, when we say that the reaction rates are much infinitely faster in compared to diffusion, so that there is no reactant leakage, and as a result of that these things are 0. So as to put it in formally, we say that yf tilde is equal to 0 between xf tilde when x lies between xf tilde and x and 1. So of course we can non-dimensionalize x as is equal to x by L. Okay. So so x tilde reaches 1 when x equal to L, and of course in this region, since oxidizer is equal to 0, your mass fraction of the oxidizer is equal to 0 when between 0 and x, when x is between 0 and xf tilde. All right. So now then we can apply all these equations and get basically the we can apply this. We can do this using this. This and this, we can essentially obtain the temperature because your y's get eliminated in this right sides, and then we obtain the temperature on these two sides as this and this. That is, the temperature in this side is given by this equation, and the temperature on this side is given by this equation. But the most important thing to note is that the temperature is linear in x. T tilde is linear in x tilde. Okay. Now that is why where does this come from? This comes from the fact that this is essentially a diffusion problem. So and it's essentially we are solving for the Laplace equation, and applying proper boundary conditions, we essentially find that the beta I is essentially linear in x. That's where it comes from, because the solution of Laplace equation, when you have boundary conditions like this, it gives you linear solutions. Okay. So then of course we can also, when we incorporate this temperature equation back into the beta I equation, we also get equations for this yf tilde and y0 tilde, and those are also given by linear in x, and this is essentially the profile we get, that this decreases like this, whereas the y0 decreases like this, and the temperature increases like this and decreases like this. So what is one point is clear here, that in the whole domain, the maximum temperature point is that T is at T equal to xf tilde. So this is the point where the temperature is maximum, and but then that completely solves the problem. So you see how straightforward it is, that just by this whole coupling function, this problem contained all the complexities, right? It contained the reaction rate, etc., but we just remove those things by just considering the fact that your coupling function formulations, and as a consequence of Lewis number equal to 1, and using that we just solved this whole thing in just one step, okay, by forming a Laplace equation out of this complicated diffusive reactive equations. Okay, so that is the strength of coupling function formulations. Yes, it requires some time to properly normalize them, properly stoichiometric weight them, etc. But once those things, those parts are done, we can just get the solution in one step, and that is the power of normalization also. So this is strongly encouraged that you solve these things in this kind of in this manner, instead of going through the full dimensional form or going through the full diffusive reactive equations. Now the interesting thing is that what needs to be noted is that if we set that yf tilde is equal to 0 and or y tilde equal to 0, then we can, using these two things, we can find out what is the location of the flame, that is what is xf tilde. So that gives you basically xf tilde, and we find that the xf tilde is nothing but this yf0 tilde divided by yf0 tilde plus 1 y0 l tilde. Now this is equal to 1, so this becomes essentially 1 by 1 plus yol tilde, which is essentially given by the phi star, that is equivalence ratios, normalized equivalence ratio is equivalence ratio star divided by 1 plus phi star, and which is essentially the normalized equivalence ratio. So essentially the flame is stabilized at the normalized the x by L, xf by L is essentially phi star, which is the normalized equivalence ratio of the fuel air mixture that we have. Okay, so that is the thing. And we can also find out because we know the gradients, we can also find out what is the fuel mass, fuel consumption rate, and that is given by this thing, that is minus lambda by Cp is equal to dyf df. If you are surprised, this essentially what we have done is that we have just replaced the rho d dy by df with lambda by Cp, because our assumption Lewis number is equal to 1. So that is why we can do this switching between rho d and lambda by Cp. Alright, so that is what we have obtained, and then we can also show what is the criteria of mass maximum burning when yf0 is obvious, is that yf0 is equal to and yf0 is equal to 1, but that is when you have pure fuel and pure oxidizer, then you have maximum burning. And the final thing is that how to obtain the flame sheet temperature. Now since we know the xf star location, we can substitute this in the temperature in the temperature equation, and what we get is essentially this form. That is, if we substitute this xf tilde in either this one that we have obtained as in either these two equations, 5 or 6, which was the temperature equations, we could easily recover the temperature. That is, this was the xf tilde equation that we have got, and then what we can get is that we will get this equation, that is T. Actually, I'll just write in the next sheet. This is, that is, if you this needs some discussion, that how to get the temperature. Substitute in temperature equations, we get Tf tilde minus T0 tilde. That is, what I want to say is that if you substitute this thing, okay, in these equations, that is in the temperature equations, where you see that T minus this is in this part, T minus is essentially T0 tilde plus TL tilde minus T0 tilde plus YOL tilde times X tilde. That is, if you, instead of X tilde, if you substitute XF here, okay, XF is a function of what, 1 by 1 plus YOL tilde. Similarly, that in this thing, if you substitute XF here, okay, which, and then the similar things, and then if you substitute the other values of this YF, Y0, etc., what you will get finally is this form, that is TF minus T0 tilde divided by YF0 tilde plus Tf tilde minus T0 tilde divided by y0 L tilde is equal to 1. Alright. Now what are all these things? Now yf tilde is equal to yf divided by yf 0. Okay. Similarly, y0 tilde is equal to y0 divided by sigma 0 yf 0. Okay, and qc is equal to summation y is equal to 1 to okay. So, and essentially sigma 0 is given by w0 times sigma 0 double dash minus sigma 0 dash divided by wf yf double dash minus yf dashed. Okay. If you now substitute all these things here, what you will get is that you Tf tilde oh, by the way, the Tf tilde is given by Cpt divided by yf 0 qc. Okay, and if you substitute all these things into here, all these things goes if you substitute here. So essentially what we have done is that we have substituted xf tilde equation in the t tilde equation, right, and then all these normalization, this weighting functions, if you substitute back here, what you get is essentially Cp by yf 0 qc Tf minus T0 divided by yf zero. This is actually equal to 1, but anyways, plus sigma 0 divided by y0 L times Tf minus T0 is equal to 1. You can just do the normalization in this. Okay. So now, of course, these two cancels. Okay, and this is QC. If we now we can write this as, then this implies Tf minus T0 plus sigma 0 times yf 0 by y0 L times Tf, sorry, this is TL tilde is equal to QC YF by CP. Okay, this is what you get. Okay, let me just put it here itself. So this gives you the flame temperature, that is what is the temperature at xf, that is T at xf is equal to Tf, and that is given by this equation. Okay, that is the temperature at xf is given by Tf minus T0 plus sigma 0 times yf 0 divided by yol times Tf minus TL plus QC YF by Cp. All right. Now what does this mean? What does this significance? Now to understand the significance, on the right hand side you see what you have. On the right hand side you have QC, that is a chemical heat release, okay, and which is given by this times YF, that is it is the heat release that is you get by burning YF kg of fuel, alright. Now what does that do? Where does YF come from? YF come from the fact that in the mixture that you have considered, the fuel mixture, on the left hand side 1 kg of fuel mix is a short form mixture, we can write, contains YF kg fuel, agreed, alright. So that is where YF come from. So basically this amount of heat release you can get by burning is in terms of basically 1 kg of fuel, 1 kg of fuel mixture. So QC times YF is this thing, okay. So 1 kg of fuel contains YF kg of 1 kg of fuel mix, consider the word fuel mixture, contains YF kg of fuel. Now similarly for stoichiometric burning, what do you need? For stoich burn, WF times nu F double dash minus nu F dash kg fuel needs W0 times nu 0 double dash minus nu 0 dashed kg oxidizer, okay. All right. Now so for stoichiometric burning, this amount of kg of fuel, pure fuel, needs this kg of oxidizer, okay. Then it means that 1 kg of fuel needs W0 times nu 0 double dash minus nu 0 dashed divided by WF times nu F double dash minus nu F dashed kg oxidizer, okay. And if we just replace this with YF, then this needs YF kg of oxidizer, okay. Now what is this? This is nothing but YF sigma 0, where sigma 0 is nothing but this, okay. So now YF kg of fuel was contained in 1 kg of fuel mixture, therefore 1 kg of fuel mix needs YF times sigma 0 kg oxidizer, alright. Now Y0 kg oxidizer you get in 1 kg of oxidizer mixture, right, because on the right hand side you have basically Y0 is the fuel mass fraction of the oxidizer, okay. So this amount of oxidizer Y0 times YF times sigma 0 kg oxidizer, which is needed for stoichiometric burning, okay, in sigma 0 YF by Y0 kg of oxidizer mix. So what you get is that for stoichiometric burning 1 kg of fuel mix needs sigma 0 times YF by Y0 kg of oxidizer mixture. Okay. This is very important to understand. So, just please go over this once again. That is, what we have done is that 1 kg of fuel mixture contains YF kg of fuel, alright, on the left hand side. Now, for stoichiometric burning, WF times this kg of fuel needs this kg of oxidizer. Therefore, YF kg of fuel needs this kg of oxidizer, which is nothing but sigma YF times sigma 0. Now, you find Y0 kg of oxidizer considering the right hand side now, Y0 times sigma Y0 kg of oxidizer in 1 kg of oxidizer mixture. Therefore, this amount of, where will you find this amount of oxidizer mixture? You will find YF times sigma 0 kg of oxidizer mixture in sigma 0 times YF by Y0 kg of oxidizer mixture, alright. So, for stoichiometric burning, 1 kg of fuel air mixture essentially needs sigma 0 times YF by Y0 kg of oxidizer mixture, okay, because on the left hand side and the right hand side both contains inerts, that is the whole point, okay. So, for stoichiometric burning, 1 kg of fuel mixture contains sigma 0 times YF by Y0 kg of oxidizer mixture. Now, going back into this, what is this doing? This is considering per kg of fuel mixture. So, if you have 1 kg of fuel mixture, this is the amount of heat is being released, okay, which is the standard heat release in 1 kg of mixture, UC times YF, and that is doing what? That is heating up 1 kg of the fuel mixture from T0 to Tf, okay, and it is also heating up exactly the amount that is required for stoichiometric burning, exactly the amount of oxidizer, that is oxidizer mixture, that is required for stoichiometric burning. So, this heat release, it is doing the job of heating up 1 kg of fuel mixture and this is also heating up the exact amount of oxidizer mixture for stoichiometric burning, okay. So, then what is the flame temperature? Exact, then it says that at the flame what is happening is stoichiometric burning is happening, because at the flame your temperature is raised from T0 to Tf and TL to Tf, and this amount of heat is released, is heating up 1 kg of fuel air mixture, or not 1 kg of fuel air mixture, 1 kg of fuel and inert mixture, okay, 1 kg of fuel mixture and the exact amount of oxidizer mixture which is required for stoichiometric burning. So, the burning that is happening in the flame is essentially stoichiometric burning, and the flame temperature, corresponding flame temperature, is essentially the adiabatic flame temperature, alright. So, this proves that the flame temperature in a non-premix flame is essentially the adiabatic flame temperature, okay. And this is the one of the most important hallmarks of a non-premix flame, that the temperature, unless there is strong reactant leakage, okay, that is the flame temperature is exactly the adiabatic flame temperature. You have no control over it, because the mixing at the flame is always at the stoichiometric is at a stoichiometric proportions, and the flame itself stabilizes at a location where it's exactly the fuel air mixture is at a stoichiometric proportion, okay. So, the temperature, the mixing is, the burning is stoichiometric, and the temperature thus reached is also the adiabatic flame temperature. So, that you cannot control the temperature, and because you cannot control the temperature, you cannot control the emissions, and also you have soot and a lot of NOx because the temperature can be so high. So, this is one thing, one very important thing about a non-premix flame, that the temperature reached is always the adiabatic flame temperature, and you can clearly show that, find it from this equation, that the flame temperature reached is why the flame temperature reached is the adiabatic flame temperature. But I suggest you go through the book also, and you go through this derivation once again to convince yourself that this is the case, alright. So, that is for this class, and we will meet again to discuss the Stefan flow, that is liquid evaporation and then droplet evaporation and condensation. So, thank you.